All right, let's talk about the equilibrium constant calculations. The first thing we're going to look at is calculating the equilibrium constant itself. All right, so in a problem of this sort, you will literally be asked to find the equilibrium constant. In order for this to be possible, you have to be given the concentrations of all the reactants and products at equilibrium. So notice here that I have brackets BRCL and a subscript EQ, implying that this is the equilibrium concentration of BRCL. Same thing for BR2 and the same thing for Cl2. We have the equilibrium concentrations. So all you have to do is, based on the balanced equation, write out the expression for the equilibrium, which will be Br2 times Cl2 divided by BrCl square. And just make sure that you're not including things that are solids or liquids. Okay, so we have Br2 to the first power times Cl2 to the first power divided by BrCl to the second power. Okay, and now we enter the actual equilibrium concentrations into the expression. So Br2 is 5.76 times 10 to the negative 6. So we include that in the expression. There you go. Boom. Now Cl2 is 9.82, right? Times 10 to the negative 4. So we enter that in here. And then the BrCl is equal to 1.23 times 10 to the negative 2. So we enter that into the expression. And don't forget that this needs to be squared since the balancing coefficient is 2 for BrCl. So what I would recommend here is that you definitely use parentheses for your multiplication and divisions. Otherwise, things can get a little messed up. If you like, sometimes I like to do this semi-backwards. Like I'll take care of the denominator first. I will square that number. And once I get that answer, I write 5 in parentheses, 5.76 times 10 to the negative 6, close parentheses, divided by answer. Basically the calculation I did previously. Press enter and then multiply that new answer by 9.82 times 10 to the negative 4. That will basically give you the following. You could also, of course, multiply first and then divide. It's totally up to you. But at the end, you should end up finding out that the equilibrium constant ends up being 3.75 times 10 to the negative 5. So just be cautious with exponents. I really can't overemphasize how important it is for you to use parentheses um, to avoid confusions between you and your calculator. Right? So use parentheses to make it obvious to the calculator that the 1.23 times 10 to the negative 2 is the whole number. All right, so that's the equilibrium constant. Now we're going to do another one. This one is a little bit more complicated. We're going after the equilibrium constant still, and we have the equilibrium concentrations of every species that is AQ. Notice that in the equation, water is also present as a product, but water is a liquid. We don't actually use it in the expression, so you don't have the concentration of water, even though I already show you how to calculate it if you wanted to. But what we're going to do is we're going to input everything that's AQ. So we have, first of all, we have magnesium 2 iodide. We have a coefficient of 2 in front, so we're going to keep track of that. But first, we're going to place magnesium 2 iodide, and we're going to raise it to the second power. Then we move on to KiO3. We have that as a product, so that has to appear on the product side, so on the numerator of the fraction, and we're going to raise it to the second power. Water we ignore because it's a liquid, so we move on to the next one, right? So don't include this in the expression. Move on to Ki. Ki has a balancing coefficient of 1, so you simply just multiply by Ki. And that's it for the products. Now, look at the reactants. You have Hi as a reactant, but you have a balancing coefficient of 4. So that means that you have to divide by the concentration of Hi raised to the 4th power. Likewise, next reactant is Aq, potassium permanganate. This particular substance, you want to place on the denominator, and you want to raise it to the second power. Okay? And the last one, Ki3. You want to bring this molecule down here and raise it to the first power since it only has a coefficient of 1. Alright, so now we have the entire expression arranged for us. All that's left to be done is to plug in the values of the equilibrium concentrations. So let's start with manganese 2 iodide. That concentration is 1.23 times 10 to the negative 3. So we're going to input that, and don't forget to square it, right, as it should be based on the expression here. Then for KiO3, the concentration, equilibrium concentration is the one shown here. So we're going to input that, and we also need to square it. And finally, we're going to multiply this by the concentration of Ki, which is shown right here. That's raised to the first power. So we input that information. And now we're going to divide by the concentration of Hi to the fourth power, which is 7.86 times 10 to the negative 3 raised to the fourth power. We multiply this by the concentration of potassium permanganate raised to the second power, which is 5.617 times 10 to the negative 7. And we multiply this by the concentration of Ki3, which is 0.00235. All right, at this point, you're going to have to carry out a few squares, so I recommend that you take care of the squares first. So 1.23 times 10 to the negative 3 square, 5.76 times 10 to the negative 6 square, 3.86 times 10 to the negative 3 to the fourth power, and 5.17 times 10 to the negative 7 to the second power. So if you take care of those four numbers, you're going to get the following expressions. And now you just have to multiply 1.51 times 10 to the negative 6 times 3.32 times 10 to the negative 11 times 0.186, all divided by 3.82 times 10 to the negative 9, divided by 2.67 times 10 to the negative 13, and divided by 0.00235. You should find out ultimately that this equals 1.49 times 10 to the third. Now you could also do what I did right here, which is take care of all the multiplications in the numerator, write down the value. Take care of all the multiplications in the denominator, write down the value. Although I would recommend you to include maybe 4 decimal places for each of them so that you don't introduce enough error in your calculation that you are off from the answers that you ought to be putting down. All right, so that's how you calculate the equilibrium concentration. Let's now look at the determination of the concentrations, the equilibrium concentrations of some of the species. So in this example, I am asking you to determine the concentration, the equilibrium concentration of BrCl. We are being given the concentration, the equilibrium concentration of Br2 and that of Cl2. And we also have been given the equilibrium concentration. So basically we have everything in here except for the concentration of BrCl. So in order to solve for it, what you first need to do is multiply both sides by BrCl square, right? First of all, we write the expression. That still needs to happen. Once you have the expression, we're going to solve for BrCl. So multiply by BrCl square, divide by the equilibrium constant, and since you want the concentration of BrCl, you have to take the square root of both sides. All right, so now you input the values. So here we go. The equilibrium constant is 3.75 times 10 to the negative 5. So we input that in here. The Br2 concentration is 3 times 10 to the negative 2. So we're going to input that in the expression. And the Cl concentration is 1.25 times 10 to the negative 1. So we input that as well. And here we do our typical thing. Multiply 3 times 10 to the negative 2 by 1.25 times 10 to the negative 1. Press enter. Divide by, in parentheses, 3.75 times 10 to the negative 5 and press enter. And that answer, what you want to do is take the square root. So write square root, answer, press enter, and you should find out that ultimately the BrCl concentration, the equilibrium concentration, has to be 10 molar, which is actually pretty high, all things considered. All right. So there's one more thing that we need to discuss in terms of calculations. This is going to be the slightly more robust version of the equilibrium calculations. So I'm going to only focus on the solubility product constant. This is a very specific equilibrium reaction. Specifically, this is the dissolution of a salt. The salt dissolves in water, but there could be only a partial extent to which this happens. In fact, if the salt that you start with is considered to be insoluble, here for sure, add the solid to the water, you're not going to expect the solid to dissolve. However, there's going to be some small amount of that salt that actually does dissolve in water, providing a saturation level to the solution, but most of it's going to remain as a solid. So what we're going to do is determine with an equilibrium calculation how much of that solid is actually turning into the soluble aqueous species. And the idea is that when you look at your insoluble salt, you have to pay attention to the stoichiometry. The reactant is going to be the solid itself, and the products are going to be the corresponding cations and the corresponding anions with the proper proportions. So if you have excuse me, so you have A number of cations, you're still going to have A number of cations. If you have B number of anions, you will still have B number of anions. And we will write out the equilibrium product constant for this stuff. And the beauty of this reaction is that since the reactant is going to be a solid, you will not have reactants, and by default, you will not have a denominator to worry about, right? So the solubility rules will kind of help you out to decide whether a salt is to be insoluble or not. And if so, then there's going to be a solubility product constant expression to derive how much of it actually dissolves in water. All right, so let's do the calculations. Let's go into the molar solubility. All right, so let's say that we have silver chloride, which we know that it's going to be insoluble in water. But now we're being provided with the equilibrium constant, the solubility product, or KSP equilibrium constant of AgCl, which is 1.77 times 10 to the negative 7. All right, so AgCl, if it's to split up, first of all, you start with it as a solid. If it splits up, it has to split up into the corresponding cation and the corresponding anion, in which case you're dealing with Ag plus Aq and Cl minus Aq. Those are the components of AgCl. And since you only have one of each, the balancing coefficients are 1 for both. Alright, so all you do is set up a table, which we call an ICE table. And the ICE stands for initial concentration, changing concentration, and equilibrium concentration. And what you do is you start with the initial amount. Now, when you basically are asked to determine the solubility, automatically the concentration, the initial concentration of Ag plus and Cl minus is going to be 0. You have none of it. Oh, and by the way, there are actual places, there's actual parts where you can go to that have everything made out of ice, and they do have ice tables in there, which I think is kind of cool. But anyway, the initial concentrations are going to be 0 because you have no ions to begin with prior to you adding the salt to water. But then there's going to be a change in concentration, which is based on the quantities of the products that you have here. You have one silver plus being formed, so whatever the change is, call it X for the time being. You're going to be increasing the amount of Ag plus by a plus X amount. And the amount of chloride will also be increased by a plus X amount because you only have one of each in the product side. And then the equilibrium concentration is simply the addition of the initial concentration row with the change in concentration row. So the equilibrium concentration will simply be X for both of them. So what you do now is you set up your KSP expression, which is going to be simply the products raised to their balancing coefficient. So you'll have silver to the first power times chloride to the first power. And right now we know the equilibrium concentration to be equal to X for both. So 1.77 times 10 to the negative 7, which is the equilibrium constant, must equal X times X, which is X squared. So right here, all you need to do is take the square root of the number, and that will give you the value of X. And this is what we will say, this is the maximum solubility of silver plus, 1.33 times 10 to the negative 5 molar for both silver and chloride. This is the saturation level. Okay, this is how much you expect to get, and no more than that, just by dunking some silver chloride solid into your water. All right, let's do another one. Here we're going to determine the solubility of cobalt 2 sulfide, which has a KSP of 5 times 10 to the negative 22nd. So we start with the solid, cobalt 2 sulfide, which we expect to produce only one cobalt 2 plus and only one sulfide 2 minus. So we do the same thing. We set up the ice table. Initially, you have no concentration of either of those ions. The change is based on the balancing coefficient, 1 to 1 for both, so X and X. So the equilibrium concentration, which is the sum of the two rows, is going to be X for the two of them once again. And because the KSP is based on the products only, right, the reactants are solid, so you never even include it in the expression, you end up with the cobalt concentration to the first power times the sulfide concentration to the first power. And in this case, 5.0 times 10 to the negative 22nd has to equal X squared. So if you take the square root of both sides, you'll find out that X equals 2.23 times 10 to the negative 11. And that means that the equilibrium concentration for both cobalt and sulfide is very small. We're basically talking about 22.3 picomolar, which is, that's very small. Like, you might not even be able to measure that because it's that small. But this is the saturation level. That's as much as you can have in solution before the cobalt and the sulfide start precipitating out as a solid. All right, one more example to do this. This is the last call, right? Ice table on the rocks, the last call. We are going to do the same stuff, but here pay attention to the subscripts. This is copper 2 hydroxide, and now you have a 2 in here because of the copper 2 plus. Alright, so that's still your solid, and this will generate your cation, which is your copper 2 plus, but now you're generating hydroxide, and there's 2 hydroxides present in your salt, so you end up with 2 hydroxides as well. Now this changes the picture ever so slightly because the coefficients are no longer 1 and 1. Now you have a coefficient of 1 for copper and a coefficient of 2 for hydroxide. So when you set up your ice table, the initial concentrations are 0. The change for copper will be plus x, but the change for hydroxide is going to be plus 2x because now you have a coefficient of 2. So for every 1 copper that you produce, you ought to be producing 2 hydroxides, and that's represented by the x and the 2x. So adding up these two rows gives you x as the equilibrium concentration for copper and 2x for hydroxide. Now setting up the expression, the KSP expression, you basically have copper raised to the first power, but you're going to have hydroxide raised to the second power, right? So don't forget, you still need to incorporate that into the equilibrium expression. And here, you now input the values of the equilibrium concentrations, x for copper and 2x for hydroxide. So the 4.8 times 10 to the negative 20 will equal x times 2x squared. And 2x squared is the same thing as saying 4x squared. And 4x squared times x is the same thing as saying 4x cubed. So to solve for x, what you will need to do is divide both sides by 4. And once that's done, you're going to have to take the cubic root of both sides. Or conversely, you could raise the number to 1 over 3. But the cubic root, that's the same thing. So in this case, we find out that the equilibrium concentration is 2.29 times 10 to the negative 7 for copper. But for hydroxide, it's actually twice that value, right? So you have to go back to this table and, make sure to input the x into the table. So we're not going to have 2.29 times 10 to the negative 7. Instead, we will have 4.58, right? 4.58 times 10 to the negative 7. There we go. So those are the equilibrium concentrations, and this is the maximum saturation value for copper 2 plus and hydroxide. So just be aware of those balancing coefficients. They will change your change in concentration, and they will also change the exponent of your equilibrium expression. All right, with all that being said, we have finished talking about how to do equilibrium calculations to the full extent. And in the next video, we'll talk about Le Chatelier's principle that is a little bit more qualitative in scope.